Hello, and welcome to Module 9.2c, Transformations of Exponential Functions. Our objective for today is that I can apply translations, dilations, and reflections to exponential functions. Example 12 here is multiple transformations of exponential functions. So our complete form of the exponential equation is y equals a times b to the x minus h plus k. So what does all this break down to? If we focus in, B is going to tell us whether we're growth or decay. If B is greater than 1, it is growth, means we are multiplying by something greater than 1 every single time. We are getting larger every single time. If it is between 0 and 1, we have decay, where it is getting smaller and smaller each time because we're multiplying by a fraction that's less than 1. We're doing less than 100% of it. A is going to determine if we're stretching. The absolute value is greater than 1. If it's a compression, its absolute value is between 0 and 1. And again, it's the same principle. If we're multiplying by something greater than 1, we are getting bigger and bigger and bigger each time. We're getting more than what we started with. If we are multiplying by between 0 and 1, we are getting less than what we started with. If A is negative, we have a vertical reflection. We are flipping it across the x-axis. If we have an h value, it is a horizontal shift. If it is positive, we're moving to the left. If it is negative, we are moving to the right. And lastly, k is a vertical shift. Up is positive, down is negative. So we are going to have to bring all of this together in graph these next couple of equations. So step number 1, identify the parent function. That tells us what we are starting with. Step 2, fill out the table. So filling out a data table is a great way of setting this up. Step number 3, identify the vertical or horizontal transformations and mark the coordinate plane accordingly. And then lastly, step 4 is to graph the exponential function based on the new x-axis and y-axis. So what are we doing? Let's look at our setup here. We have y equals 2 to the x plus 1 power minus 3. And when we set this up, what is our parent function? Well, it's going to be, if we strip away all of the superfluous stuff, and it is just going to be y equals 2 to the x power. That's our parent function. So when we substitute this in, let's figure this out. Let's get some data points to work from. If we put in a negative 2, we get a 1/4. If we put in negative 1, we get 1/2. 0 is to the first, is 1. 1 is to 2. And 2 squared is 4. Okay, so what is y prime? Y prime is going to be our translated version. So let's substitute our points in and see what we get. So if we have negative 2 plus 1, that's negative 1. So 2 to the negative first power is 1/2. Minus 3 is negative 2.5. Our next one, we have negative 1. Our y value is, we substitute in negative 1 for x. So negative 1 plus 1 is 0. Anything to the 0 power is 1. 1 minus 3 is negative 2. Next up, we have 0. 0 plus 1 is 1. 2 to the first power is 2. Minus 3 is negative 1. Next up, we have x of 1. So 1 plus 1 is 2. 2 squared is 4. Minus 3 is 1. And we have 2 plus 1 is 3. 2 to the third power is 8. Minus 3 is 5. So what's happening? We're transforming. We're going down 3, and we're going left 1. So let's draw in our original function, shall we? And we're going to do that one in red because that's the color I wrote in. So -2 is at the 1/4. -1 is at 1/2. 0 is at 1. 1 is at 2. 2 is at 4. And then we could even put in 3 and 8 because we know that's what that is. So our line, when we draw it in, is going to look like this. Okay, now our second one we have in green here, so we're going to draw that in. So at -2, we're at -2.5. At -1, we're at -2. At 0, we're at -1. At 1, we're at +1. At 2, we're at +5. And at 3, we would be at positive, or no, yeah, that's where we're at. So now we can graph this. And our graph goes something like that. So what are some things that we notice? Our asymptote, right? Our asymptote was on the y-axis originally, and now that has shifted down 3 units because we moved everything down 3, right? And our whole graph shifted to the left 1 space. So that altered everything. So we moved down 3 and to the right 1, to the left 1. All right, let's take a look at our next page. Again, we're going to follow the same process when we have dilations and reflections involved as well. So we identify the parent function. Followed by filling out the table based on the parent function. We're going to identify the vertical and or horizontal transformations. We're going to identify the dilations and or reflections. We're going to apply the dilation and or reflection to the y values on the table, and then graph it. So we have a function that has everything in the kitchen sink thrown into it. Y equals -2 times 2 to the x minus 4 power plus 1. So let's just go back. What is our base function on this? Our base function is y equals 2 to the x power. So let's start by figuring that out. We know we've got a 1/4, we've got a 1/2, we've got a 1, 2, 4, 8, 16, 32, 64. Now, can you graph half of these points? No, you can't. But we're going to graph what we can. So we have -2 and 1/4. We have -1, 1/2. We've got 1, 1 and 0, 1. We have 1, 2, 2, 4, 3, 8. So we have our parent function right there. And I missed a little bit on the last point, but you get the gist of it. So what all transformations do we have going on here? So I know we're going to the right 4. We're going up 1. We have a vertical reflection. And we have a stretch by 2. So all kinds of stuff is going on. So we are flipping it, we're moving it up, we are moving it to the right, and we're stretching it. So it's probably going to be a little bit easier for us to deal with this on with data tables instead of trying to manage moving all of these pieces on our graph at one time. Because you've got to flip it to the other. Let's just take, for example, our point at 1, right? We would have to move it to the right 4, so that point goes to here, and then it's going to go, we need to multiply it by, or we take the invert, or the opposite, so we go down to here, and then we multiply it by 2, so now it goes to here, and then we shift it down, or up 1, and it comes back to here. So we've got a whole lot going on here. Let's do this by the math of it, and then we can graph these points. So if I substitute in -2 to this whole thing that we have going on here, what am I going to get? I'm going to get 0.96875. If I substitute -1, and I'm going to let you guys do the math on that, I'm going to get 0.9375. You can do this work on a calculator. You can do it piece by piece in your head. Either way, you're going to get these values. 0, an input of 0 is going to get me 0.875. An input of 1 is going to get me 0.75. An input of 2 gets me to 0.5. An input of 3 gets me a point of 0. An input of 4 gets me a -1 value. Input of 5 gets me a -3 value. An input of 6 gets me a -7 value. So let's graph what we can, because some of these are just such minute changes, we're not actually going to be effectively graphing them. So at -2, we're at, right up against 1, slightly below for -1, slightly below for 0. For 1, we're at 0.75, so we're still not getting much movement. Then we were at 0.5, and these are all really rough approximations. 3 gets to 0. That's the first time we're hitting a whole number. 4 gets us to -1. Now we can see how the shape of this one is starting to shake out. When we go to 5, we drop down 3, so now we're down to there. 6 is down to -7. So you'll see why I added in all those other ones that we weren't actually going to be able to graph on the original. But now we see our graph looks something like this. Okay, so now our original axis of symmetry, not axis of symmetry, our original asymptote was at y equals 0. And our new one, this was affected by our vertical change, is at y equals 1. Actually, let me do that with red. So our new asymptote is at y equals 1. So let's kind of go through all of these things that have happened, right? We started off at, let's pick that point of 0. And I'm going to use my laser pointer. And I'm going to just, actually, no, let's use 1 or 2. Let's use 2. So the 0.24, right? This point right here. What we start by doing is we are going to shift it to the right 4. So we're going to go 1, 2, 3, 4. Then we are going to flip it to the negative side. So we're going to go negative on it. So we're going to go down to -4. Then we multiplied it by 2, which brings us to -8. Sorry, -9. And then we go up 1, and we get to where we are at -7. So you can see how these have kind of, it's messed with it a little bit, right? The last step that we did was the +1, because that's the only thing that's not being multiplied and divide or multiplied by that whole original piece, right? So we moved to the right 4, and then we became -4, and then we doubled it to -8, and then we came back up to -7. So you can see how that one point, we went from here to here based on our transformations. And all of the other points corresponded with it. Okay. So on the next page, we have 6 problems that we're going to work through. And all of these 6 problems have the exact same parent function. We are all working off of the basis of y equals 2 to the x power. So we have our graphs here. And so let's go through. We're going to do a couple of these as a group, and then we're going to do a couple of these using as you try problems. So I'm always going to add in these extra 2 points of 4 and 8 on this graph, and then we are going to go from there. So identify what are the things that are happening here, because there could be multiples. The first thing is we have a -2 there. We have a +3 here. So we're going to the right 2, and we're going up 3. So each point is going to go to the right 2 and up 3. So let's do that. We go right 2 and up 1, 2, 3. To the right 2, up 1, 2, 3. To the right 2, up 1, 2, 3. To the right 2, 1, 2, up 1, 2, 3. To the right 2, up 1, 2, 3. So it puts it a little bit above our graph there. So our new function looks like this. Okay, and you'll notice again, our new asymptote has gone up 3, right? The graph moved up 3, so the asymptote moved up 3. Letter B. We have y equals -2 to the x minus 2 power. So I have a -2 there. I've got a negative out front. So we're going to go right 2. And what's happening? We have a vertical reflection. All right. So we're going to go to the right 2 and flip it down below. So let's, and I'm going to add in my extra points here because I always like to have those 2 extra points to work with. So if we're going to take that point to the right 2, so we're going to go right 2, so from 3, 8, now it's going to be at 5, 8, and we flip it across the x-axis, it's 5, -8. Our point at 4, we're going to go, and we can do this with a real thin line, we're going to go to the left 2, or to the right 2, and then we're going to move it to the other side of our axes. We're going to mirror it to right there. Okay. Let's see. Let's go with this one. We're going to go right 2 and flip to the other side. And so we have a point right there. We're going to go to the right 2 and flip to the other side. To the right 2, flip to the other side. And am I off completely? My first point that I placed was off. That's why. So it's on that line. There we go. So now, again, we draw our line in, and we see this reflection and shift to the right. Again, we have that exact same asymptote because we didn't actually shift up or down. We moved to the right instead. Okay. All right. Letter C. We have y equals -2 times 2 to the x power. So one of our options, or so one of our transformations, we have a negative, and we now have a number out in front because we really haven't done much of that, both of these at the same time. So we have a stretch by 2, and we have a vertical reflection. So we're going to stretch by 2, and we're doing a vertical reflection. So each point is going to flip across and get further. So when we have 1/2, multiply that by 2, and we get 1. We have 1, multiply that by 2, we get 2. 2, multiply that by 2, we get 4. Our other 2 points that we work with, we have 4 and 8. 4 times 2 is 8, and our 8 times 2 is 16. We won't be able to show that. All right, so we stretched it out, still have the same asymptote, and we have our graph there. All right, now we have letter D. Letter D is giving us negative 2 to the x power minus 3. So we have down 3, and we have vertical reflection. All right, so we're going to flip it, and then we're going to shift it. So positive 1/2 becomes negative 1/2, and then we go down 3. So 1, 2, 3. So we get negative 3.5. Positive 1, we flip it, becomes negative 1, and then we go down 3, and it's at negative 4. Positive 2, we flip it, it's negative 2, moves down 3, it's negative 5. Positive 4, we flip it, it's negative 4, we move down 3, it's negative 7. Positive 8, we flip it, it's now negative 8, we move down 3, it's negative 11. So approximately there. And so now we can graph our line in. Notice our asymptote moved, right? It is down 3 from where it was. So that's one way. If you're a little struggling on the up and down movements and having that line, go ahead and draw in an asymptote with a highlighter. I want you guys to try letters E and F on your own, and then you're going to check your work against mine. All right, letter E. What are my pieces that I'm working with here? I've got a stretch and I've got a shift. So we're doing a stretch by 3, and we are moving down 6. So let's see what happens for each of these points to stretch them by 3 and move them down by 6. So 1/2 times 3 is 3/2, and we subtract 6 from 3/2, and we are going to have a point at negative 4.5. So a little bigger point there, right? So 3/2, otherwise known as 1.5, minus 6 is negative 4.5. So now 1 times 3 is 3, minus 6 is negative 3. We've got 2 times 3 is 6, and 6 minus 6 is 0. We have our points that we like to work with of 4 and 8. So 4 times 3 is 12, minus 6 is 6. And will we be able to do anything? 8 times 3 is 24. 24 minus 6 is too high for us to deal with. Okay. So we see that our graph is following along this pathway here, and our asymptote is at negative 6. And I probably could have picked some more of those negative points to help us out a little bit with that stretch of 3, but we didn't need to. All right, letter F. Letter F gives us the function y equals negative 2 times 2 to the x minus 2 power minus 3. So we have a whole bunch going on. So we have we're going 2 right, we're going 3 down, we're going vertical reflection, and we have a stretch by 2. So we've thrown everything into this problem. So let's start with what we have, right? So we have point at, let's start with the -1/2. So when we do these, so let's do -1. So -1 minus 2 is -3. 2 to the -3rd is 1/8 times 2 is going to be 1/4, but then it's going to be negative, so it'll be -1/4, and we're shifting it down 3, so that -1 is now down at -1/4 minus 3 is -3 1/4, so it's going to be down about there. Okay, so we have anything to the 0. So 0 minus 2 is -2. So 2 to the -2nd power is -1/4 times -2 is going to be -1/2, and we're moving it down 3, so that's -3.5. We go to the first power, we'll have 2 to the -1st times -2, which is going to give us -1. Down 3 is -4. If we look at 2 to the 4th power, right, if we take the second power, 2 minus 2 is 0. Anything to the 0 power is 1, times -2 is -2, minus 3 is -5. Okay. When we substitute in 3, 3 minus 2 is 1. 2 to the 1st power is 2, times -2 is -4, minus 3 is -7. And then 4 minus 2 is 2. 2 squared is 4, times -2 is -8, minus 3 is -11. So our graph is going to look something like this. And we see that our asymptote moved down 3 places. All right, if we flip to the back page, we are going to take a look at some exponential functions that we are going to use. And this is really some just kind of real world applications of these types of functions. So an initial population of 20 rabbits triples every half a year. The function f of x equals 20 times 3 to the x gives the population after x half-year periods. How many rabbits will there be after 3 years? So we substitute in f of, and my pen doesn't want to cooperate, we have f of 3, although it's 3 years, and these are half-year periods. So we're going to take 3 and we're going to raise it to what power? So if it's half-year periods, how many half-year periods are there in 3 years? It's going to be 6. So we have 20 times 3 to the 6th power. So if we go ahead and we do that, 3 to the 6th power is going to give us 729. And when we multiply that by 20, we get, after 6 years of uninterrupted growth, you would have 14,580 rabbits. Okay, so after 3 years, so 6 half-year cycles, you would have that population triples 6 times. You had 20 originally, you end up with 14,580 rabbits, which would explain why all of my decorations get eaten every year by rabbits. So, letter B. Suppose a culture of bacteria doubles each hour. There are initially 2,200 bacteria. The function f of x equals 2,200 times 2 to the x gives us the number of bacteria after x hours. And we want to know after 5 hours, how many bacteria will we have? So we substitute in 5 for x times 2 to the 5th power. 2 to the 5th power gives us 32. And when we multiply that by 2,200, we get that there will be 70,400 bacteria. All right, now there are 2 more examples, letters C and D. Please try those on your own and then check your work against mine. Letter C, computer mapping software allows you to zoom in on an area to view it in more detail. The function f of x equals 100 times 0.25x to the x power models the percent of the original area of a map after zooming in x times. What percent of the original area is shown after zooming in 5 times? So let's look at that one first. 5 zooms, so f of x equals 100 times 0.25 to the 5th power. And so when we multiply that out, we get f of 5 is going to be equal to 0.098%, and I'm rounding there. But we have a secondary question. Our secondary question is asking us what percent of the original area is shown after zooming out 2 times. Well, how can we zoom out? Well, that would be if a positive exponent is zooming in, a negative exponent would be zooming out. So f of, we're going to say negative 2 is equal to 100 times 0.25 to the negative 2nd power. And so we get that it's going to be 1,600%. So 1,600% of the original area is shown if you've zoomed out twice. All right. Our last one, letter D. Suppose an investment of 7,500 doubles in value every 12 years. The function f of x equals 7,500 times 2 to the x power models the growth of the investment, where x is the number of 12-year periods. What is the growth in the investment if it is allowed to continue for 48 years? Well, if we're talking about 12-year periods, 48 years is 4 periods. So we're going to substitute that into our function. F of 4 is equal to 7,500 times 2 to the 4th power. And so f of 4 is equal to 7,500 and 2 to the 4th power. 2 times 2 is 4, times 2 is 8, times 2 is 16. And so when we do 7,500 times 16, we are going to get that f of 4 is equal to, we're using dollars, $120,000. So if you could get that rate of return where your money is being doubled every 12 years, you could have some significant amount of money based on just a small amount to start with. All right, so that is also factoring in compound interest and whatnot. So that is the end of our notes, not only for this lesson, but for this module. If you have any questions, please bring them to class tomorrow. Otherwise, I hope you have a great day.